Hi everyone, welcome to the fifth interaction session on the course on advanced robotics. So, I think very few people are here, but we'll continue. And then if someone joins in between, that's perfectly okay. So, last time we had seen a couple of problems on redundancy, especially for 2R manipulators. We were able to solve the problem on that and say that okay, if it is lying at the edge of workspace of 2R manipulator, then it is just you are able to just move it in one direction and not in the other direction. So instead of some ellipsoid, you actually get a straight line. So that was, and if it is in the center of the workspace, then you have a whole sphere where you can go. But uh, you saw many proofs in the lecture this time, right? That if you have the joints in the spherical, if the joints move or lie in the sphere, then your end effector actually lies in the same n dimensional hyperellipsoid. So today let's brush up all those concepts that you have done and we'll proceed with the first question. And we'll have one MATLAB problem at the end that I'll show you exactly what it is. Okay. So, yeah. A redundant manipulator has more degree of freedom than what? Uh,
6.
okay, if it has more degree of freedom than 6. And what is more degree of freedom than 6? I'll show you. Uh, let's say this is your 2R manipulator. Okay. Let's call it theta 1. Let's call it theta 2. And let's say this is your end effector. What if this is my complete workspace? I did not draw the circle properly, but yeah, this is my complete workspace. And my end effector actually lies here. So this is redundant, right? So you cannot say if a 2R manipulator, or how to explain this. What I mean is, if something has more degree of freedom than 6, then you cannot say that it is a, I mean, more degree of freedom than 6 means what? How do you define degrees of freedom? Let's come to this thing. What all degrees of freedom do we study? How much we can achieve in the environment around us? Let's say we have some NR manipulator. I'm not considering P for simplicity. Let's say we have n dimensional NR manipulator and with n revolute joints. What is the maximum degrees of freedom it can have?
N.
Does it have n? I mean, okay, I'll just wait. I'll show you. I'm searching for a video that I can show you. Just wait. Okay. Let's say we have a 3D space. Let's talk about this. Let's say we have a 3D space. What is the minimum degrees of freedom that we need to place our end effector anywhere in the space? So I'll just get clear with. Okay. So let's start with degrees of freedom. Just a second. Okay. Patient and effector. I'm talking only about in robotics terms of the robot. Okay. So this is your degree of freedom. Now, if we want to reach a point in 3D space, so this 2R will definitely go in 2D space. Let's say we had a 3R manipulator and then we want to go in 3D space. So if 3D space can be reached, how? It can, we need to move in X direction, we need to move in Y direction, we need to move in Z direction. This is all about the position. If you have linear motion, you just have translation, you can do this. Apart from this, what are their orientations? So you need to go for theta, phi and psi. So this is the minimum degree of freedom that you need if you want to travel in the workspace. Now, if you, okay. Okay, I hope I'm back. My connection was lost. Okay. So I think when you say 6, you are correct because, yeah, in this question, it is more than, so it would be correct if you say 6. So how I'm clarifying everything. So I'll tell you. Okay, I hope this is clear. And these are the 6 degrees of freedom that we need. Minimum degrees of freedom to fetch or to reach somewhere in the 3D environment around us, right? Now, let's talk about redundant manipulator at first. So, okay. Redundant. I'll today I'll ask you to make the notes of whatever I'm teaching. It will help you. So keep making notes also because all of the questions today are conceptual. Is redundant if it has more degree of freedom than the minimum required to do a given task. Now, I'll tell you why this. Okay, let's talk about other things also. So let's say there is 6 DOS manipulator. Then it has 3 position 3 degrees of freedom for position and 3 degrees of freedom for orientation, right? Then if uh, some manipulator, so any manipulator, if a manipulator has more than 6 degrees of freedom, then it is called redundant. Because why? We can also have some secondary objectives, right? What could be the secondary objectives? It could be, let's say, we want to avoid some obstacle. So it can be obstacle avoidance. It can be to avoid any singularities that we might encounter. So it can be for avoiding singularities. It can be for posture correction. Okay. So any extra degree of freedom that we have can be used for posture correction. Okay. Um, After that, the question that we have now completely depends on what task we are looking at. So if you say 6 DOF, it would not be entirely correct. I mean, you have to choose out of the 4 options, and I'll tell you why 6 DOF is not correct. But let me tell you this. Then it can be used for what? Let's say we want to optimize energy. So we want to do less tasks, and then we may have extra links and extra degrees of freedom. But my point is, let's say your task is defined as the following. Reach a particular position in 3D environment and uh, let's say we'll say that we want to avoid singularity, because you know very well, right, that when 2R manipulator has end effector here, it goes into singular configuration and you cannot just move in this direction, you just have to move in this direction. Okay, but your task was just to reach this point and do nothing, and then you have lost the ability to go from here to here without coming back, right? So you're not able to do the task. So it was entirely task dependent, right? So in this case, it is reach a particular position 3D environment and avoid singularity. When you have this question with you, how many degrees of freedom would you need? Can you say it is 6?
No, ma'am.
Right. You cannot say it is 6. It is something greater than 6. It depends in what direction you want to do. Is it only in X, it is in Y, it is in Z, whatever. But yeah, it is something less, it is something more than 6. So your task is something, and then you define what is your degree of freedom. All right. But in this question, since no task is mentioned, we really don't know where we have to reach. Okay, because a redundant manipulator for this 2R is a problem even when you have more degree of freedom than 2 if the end effector is lying here. So that is redundant. So this is not the correct option. It is actually dependent on the task. So you have been given a task, and if you have more degrees of freedom than what is required to do that task, let's say I say that no, I want to remove this. I don't want any singularity, but I just want to reach a particular position in 3D environment. Then I'll say that yeah, it's just 6 that I need. If I have any more than 6, let's say in the human hand you have 7 degrees of freedom, right? If you have any more than 6, then it is more than required what I say to do a task. So your answer should always be that whatever task I need to do, if I have more degrees of freedom than that, then that means that, yeah, my manipulator is redundant. Okay. So, okay. So if, so let's say if it is 4 DOF. So why it is, so this 4 DOF manipulator, let's say you're given a task to move in XYZ and just maintain the orientation about x-axis, then this 4 DOF will do. I mean, it is not more than what is required. So you cannot answer this. Similarly, 5 DOF is insufficient for full control in 3D space. So it is again non-redundant. You get that? I mean, you have to achieve XYZ, theta, theta, phi, and psi. 5 degrees of freedom is anyway less, so it is not redundant. 4 degrees of freedom is anyway less, it is non-redundant. 6 degrees of freedom is good, but what is a task? We don't know. So, given what is a task, we should answer this question. I hope it is clear.
Clear, ma'am. Clear.
Okay. So, yeah. The redundancy only applies when the degree of freedom exceeds what is required to do in a task. Okay. Let's move to the next question. Okay. In the case of a 3 DOF, 3R planar manipulator, so it is just going to have 3R planar. That means, what are the degrees of freedom that you'll have? Can anyone answer? It just has to be planar. Now you can think what all degrees of freedom it should have. I told you the 6 degrees of freedom are theta, phi, and psi. So let me be clear. This is rotation about x-axis. This is rotation about y-axis. And this is rotation about z-axis. And XYZ, you know already that it is just the position. Now, can you tell me if it is a 3R planar manipulator, what are the degrees of freedom it has out of these 6? It has to do everything in a plane. And I am also considering this to be my uh, x and y. Now, can you tell me? Okay. So, how you can understand this is actually, if it is a planar manipulator, then it is going to move in this plane only, right? So it is very definite that my end effector has to reach some position in xy plane, right? So 2 degrees of freedom are definitely x and y, right? And when it is moving by some angle theta, let's say theta 1, theta 2, theta 3, it is always about z-axis. So whatever I consider to be the rotation about z-axis should come here. So in this case, if I say this phi is the rotation about z-axis, then I'll write here phi. So these all are phi's and not theta. I hope that makes sense. These are the 3 degrees of freedom that we have for this 3 DOF manipulator. All right. Now, we want to answer the question, what is the order of Jacobian matrix? Is it a square matrix? Is it a symmetric matrix? Is it a positive definite matrix? Or is it a non-square matrix? Okay, let's move ahead. So, your end effector can definitely for this move in a 2D plane. Okay. And what does Jacobian do? Jacobian basically relates your joint velocities to end effector velocities, right? This is the relation that we have. So for 3R manipulator, okay, we want to derive some relation in between x dot and theta dot. So you know from this very well, right, that x is equal to uh, let's say the first link length is L1, L2 and L3. So L1 cos theta 1 plus L2 cos of theta 1 plus theta 2 plus L3 cos of theta 1 plus theta 2 plus theta 3. This is already something you know. Y will be same, just take sine. Right? We have already done this. Now, for 3R manipulator, we are considering this equation. Then Jacobian becomes what order? Can anyone answer?
2 by 3.
Right, 2 by 3. So why it is 2 by 3? Whenever you want to take out dx by dt, or I'll directly write x dot, then you differentiate dx by d theta 1, then dx by d theta 2, then y dot is equal to, or we can write this as a matrix. Let's say this complete thing is x. This complete thing is x. It is written in complex, not complex, what to say, just in a very squeezed manner. Dy by d theta 1, dy by d theta 2, right? So it is written in this way. Sorry, I missed it. Dx by d theta 3 and dy by d theta 3. So from here you can see that it is a 2 cross 3 matrix. Okay. So when you have this option, so from here you directly know, right, that it is a non-square matrix. But why is it not a square matrix? I just want to go through all the options because it helps you stabilize your concepts, internalize your concepts very well. Okay. So let's say I take the condition of square matrix. From here, from derivation, we already know, but how to strike out the wrong answers? So when it would be square, if the number of task space variables equal to number of degrees of freedom, which is usually not true for planar manipulators. Because why is it not true for planar manipulators? Because we generally consider the position. So what actually happens is, let's say we had x, y and some theta also here. Okay, and then we tried to find out a relation, which usually happens. That would be good, but we don't need, na? We already have x and y expressed in form of theta, so we do not need to find some relation. Okay, so if the number of these variables are equal to the number of degrees of freedom, then we do not need. And what are task space variables? So x dot is in task space because it is end effector position, and theta dot is in joint space. I hope this is clear. Okay, so this is the reason why it is not a square matrix. So we get a reason to eliminate this option. Now let's go to the second option, symmetric matrix. How can we say if Jacobian is symmetric or non-symmetric? So, okay, Jacobian would not always be symmetric. It can be symmetric in some cases, but that is just a coincidence, because you are actually taking the terms and then you are always having something in sine and cosine form, then you are differentiating, so you do not get the things in symmetric form. So Jacobian is not symmetric, generally not symmetric. Because the partial derivatives of position with respect to joint angles are not same, so it is definitely not symmetric. So why would we answer that? And yeah, we cannot say that Jacobian is positive definite. And how do you find what is positive definite? Can anyone tell?
If a matrix is given in square, if it is given in matrix format, then we can take the individual determinant, and if all the individual determinants are greater than 0, we can say that that matrix is positive definite.
Right, very good. So you basically take the determinant of all the minors. So if let's say you have in this way, and it is always along the uh, dominant minor. So if we take the determinant for complete for this completely, then it should be positive. If we take the other determinant for just this part, it should be positive, and then this should also be greater than 0. Then we say that Jacobian is positive definite, which also does not make sense. Why would we say that? I mean, we are not multiplying Jacobian with Jacobian transpose so that we get something of square type, right? We are not doing that. So if we are not doing that, then how it is possible? So yeah, this is also not correct. Just a second. Um, I'm moving to the next question. You can start thinking on this question.
ऐसा नहीं है, बस सही आपके आपके ऊपर आप मीटिंग में कीजिए ऐसे ऊपर का थाली मेरी क्लास में 8 बजे ही मैडम इससे जला गया पहले वाला सिस्टम नहीं है सब स्टूडेंट को मेल भी दिया ऐसा मेरा रोज भी कर रहे हैं आदेश है क्लास में बंद ही करना आपको कैसा है कमेटी तो मीटिंग और उन्होंने वक्त लेकिन से साथ आई चाबी जमा किया है ये सब बात थी कुछ करेंगे मीटिंग से साथ अभी अभी आया है
Okay. For the third question, if
Ma'am, your voice is not audible.
yeah, just a second. Just a second. Yeah. I mean, in between, maybe I'll have to shift somewhere else, but that's okay. Let's proceed with it now. Okay. If J is a non-square matrix, then the generalized solution for theta dot for the equation x dot is equal to J theta dot is obtained using what? So is it pseudo inverse of Z? It is transpose of Z? It is singular value decomposition of Z? Or inverse of Z? Okay. So um we already have this equation given x dot is equal to j theta dot, and then we want to say what is a generalized solution for this. So the transpose uh, or the svd, I mean svd is also a method to compute the pseudo inverse, but it is not the final solution, right? You might have seen this already. And the inverse of j does not exist for any non-square matrix, so that is also a problem. So you won't be able to define the inverse if your matrix is not square matrix. And for transpose, from transpose you are not definitely going to get the inverse, because again that would be a square matrix. So the only solution that you have for this is pseudo inverse, right? For generalized solution. Okay.
Ma'am, one doubt
Yeah.
regarding the previous question, ma'am. Question number 2.
Just a second, I'll move. Yeah.
Ma'am, the question is that the Jacobian of a 3 DOF manipulator, planar manipulator has dimension. So it will be 2 by 3, right?
Yeah.
Excluding the orientation of end effector.
Yeah.
Okay, ma'am.
Yeah. That is why we wrote here 2 by 3. We excluded that.
Okay. Okay.
Okay. So the question says x dot is equal to j into theta dot, where j is m cross n non-square matrix. The vectors in theta dot that get transformed into the null space of x dot forms what? Range of operator, kernel of operator, rank of operator, or determinant of operator. Okay, so do you know everything? All four that are written here. Do you have any idea about all of these? I mean, I know it was discussed, but in the lecture you were made familiar to kernel operator, right? Do you know other rank of the operator or determinant of the operator? Do you know that? Just hold on.
Not much clear.
Okay. I think I was not able to record when I plugged in the earphone. That's all right. Okay. So, okay. Let's talk about kernel first. What is kernel also called? It's called null space, right? And yeah, of a matrix J consists of all vectors theta dot such that J theta dot is equal to 0, right? So what happens in this case? Uh, this theta dot actually maps to 0 output in the null space. I mean, you have the joints moving, all of them moving, but you do not see any movement in the uh, on the side of end effector. So that is the thing that happens. I I got some problem with my microphone. I'll share the window again. Having too much problem today. Okay. So the kernel, I think I was not audible. So just I'm repeating the things again. The kernel or null space of a matrix J consists of all vectors of theta dot such that J theta dot is equal to 0, right? You have already learnt this. So what happens in this case is that this theta actually maps to a 0 output. X dot is 0. So let's say you have your hand which is 7-DOF manipulator and you are just holding this pen. Okay, when you are holding the pen, then you are actually not moving you are moving all your elbows and shoulders, but there is no effect on the end effector. If it is of this type, then it is called your theta dot actually does not map to any output in the null space. So these vectors actually represent the internal motions of the manipulator that do not affect the end effector position or orientation. And this often occurs in redundant manipulators, right? So I'll get clear with what is range of the operator. This is your range of J. It basically consists of all possible output. What is our output? It is X dot, right? That can be reached by applying J to some theta dot. So it is not related to null space. I hope that is clear. So you are going to get some output, right? And it is just a mapping from input to output. It's not related to range. Then rank of operator. Okay. Uh, it refers to the number of linearly, linearly dependence independence, right? I hope it is clear to you already because this is a part of linear algebra, columns or rows. So for Jacobian, if you try to find out what are the columns or rows, then you can just find out how many independent motions are there that affect the output, but it does not describe the null space. Okay, it determines. I'll ask you to make all these notes. These are really good concepts and you should know. Motions affect the output but does not describe the null space. Okay, and what is determinant of the operator? What will it give you? It is only defined for square matrices, right? You cannot do anything with non-square matrices. So if it is not defined for non-square matrices, if it is not defined for non-square matrices, then this is not applicable only. Okay, so correct answer is kernel of the operator. And why it is the correct option? Because it represents all joint velocities theta dot that do not result in end effector motion. X dot is equal to 0 is the main thing here. Okay, so given x dot is equal to j theta dot, j is this non-square matrix, the vectors in theta dot that get transformed into the null space of x dot forms the kernel of the operator. It is not range, it is not rank, it is not determinant. All right? Okay. Okay. Can you proceed with this question? I have to shift something and book a classroom. So I'll come back to you, but I mean, I'll stay on the call only, but just start working on this question. I mean, you can take the photo of this question and also this question. Solve these two questions by the time I shift myself. Please. Please keep on solving the question. You can also take a snip of this question, question number 7, and please solve these questions so that we can move faster. I mean, get ready with the answers. Okay.
Yeah.
Okay, I hope I am audible. We'll proceed with the questions now. Sorry for the inconvenience. So we are to start with fifth question. No, fourth we already did. Fourth question is clear, right? You understood what is range determinant. You already know what is rank of the operator and why it is kernel of the operator in which we are interested and not in the other things, because we want to uh, see how the joint velocities actually map into no motion of the manipulator. All right, now let's move to question 5. Okay. uh, so in question 5 it is in in a n-link just a second, I think, yeah, in an n-link serial manipulator, in an n-link serial manipulator, if the joint velocities are contained in the unit sphere, then the end effector velocities are contained in what? Right? You already know this, and before that I'll say x is equal to j theta dot. This is the thing which we'll always need. So you've already read it, right? And you already might know the answer. Can I get the correct answer from you, if anyone knows?
N-dimensional hyperellipsoid.
Right, very good. So this proof was already done in the classroom. So I'll tell you in a very concise way what happens here. So you already know x dot is equal to j theta, and if the joint velocities, which is theta dot, are constrained within a unit sphere, within an unit, sorry, a unit sphere, how will write it? It would be modulus of theta dot is less than or equal to 1, because it is inside the unit sphere. So the transformation by the Jacobian matrix deforms this sphere into a hyperellipsoid in the task space. Okay, and how is that defined? The shape of ellipsoid, the shape of ellipsoid is determined by the singular values. You already know this, right? किस direction में sigma ज़्यादा है is basically tells you in which direction we have the major axis and in which direction we have the minor axis. If one of the sigmas is 0, that means we do not have any extension of the ellipsoid in that direction, right? So singular values of the Jacobian matrix, and it is given by x dot is less than equal to j theta dot. Okay. From the last class you also might remember this, that each axis, these all are very important points that I am telling you. I mean, I know you all have watched the lecture and you have got all of these, but these are very crisp points that you should have with you, though you already know, I guess. To a singular value of the Jacobian, right? And the orientation, or this is not required. Let's not go into this. So yeah, you know that singular values actually help in defining the axis and all. So other options are incorrect because the first option that we had was n minus 1 dimensional hyperellipse. So it is, why it is incorrect? Because the end effector velocities exist in same dimension as the task space and not in one less dimension. Right? It has to be n-dimensional because we want to move in all the directions, and it is not as fair because Jacobian transformation scales the axis differently. It is not in equal directions all the side, so it is not sphere, it is ellipsoid. And it is not circle because circle would only apply in 2D task space and not in higher dimensions. That is the reason this n-dimensional hyperellipsoid is the correct answer. All right, now I hope you have solved this question because I was not here. So yeah, a serial link redundant manipulator. What is serial link? It means you have a fixed base and then you have all the links attached. You don't have two links coming out of the same base and meeting somewhere. So it is not a parallel manipulator, it is just a serial manipulator. So a serial link redundant manipulator is required to do the task, right? It can be controlled by task decomposition approach. This means what? Now, this means using the a serial link redundant manipulator is required to do a task. It can be controlled by task decomposition approach. This means using the least number of degrees of freedom, using all the degrees of freedom, assigning the degree of freedom to different tasks, none of the above. So let's see. We'll go through each and every option. So what is redundant manipulator? It has more degrees of freedom than required to do a given task, right? Now, the task decomposition approach actually divides the available degrees of freedom among multiple objectives, right? It can be some primary task, it can be some secondary task, as we already saw in the first question. So the primary task can just be positioning and orientation of the end effector. Secondary task could be you might need it for obstacle avoidance, minimizing energy, or avoiding singularities. Any of them can be there, or let's say some posture alignment you want to do. So this approach allows efficient utilization of redundancy by prioritizing tasks and assigning the DOF accordingly. Okay, so I mean, what is the task required and what degrees of freedom you need corresponding to that given task. So if you want to do a task, if you have less degrees of freedom, if you have least number of degrees of freedom, then it would be incorrect. And why it would be incorrect? Because redundancy involves using extra degrees of freedom and definitely not minimizing them. So if it is a redundant manipulator and it is going to do a task, it cannot have less degrees of freedom than what is required to do that particular task, right? So this is wrong. Second is using all the degrees of freedom. The thing is, because not all degrees of freedom need to be actively used. The focus is on task allocation, not just utilization. Okay, so we basically need to assign the degrees of freedom to different tasks and not use all the degrees of freedom. All right, I hope this makes sense, and none of the above is definitely not the correct answer. So this is your correct answer. Okay, let's move to the next question. I hope everything is clear from there. Now, okay, we have the global fixed frame. Global fixed frame we have, and a local fixed frame is also the thing we have on rigid body B. So we already have a global fixed frame. We have local fixed frame on body B. If the body is moving and the orientation of the rigid body is not changing with time, then it has what? So let's say this is my global frame. Okay, X, Y, and Z. There is some local frame that I have. Let's say this is X, Y, Z, and this is on body B. Right? Now, body is moving and the orientation of the rigid body is not changing. Okay, so let's say it is moving along some direction and the orientation is not changing. So then it has what? Does it have angular velocity? Does it have linear velocity? Does it have both linear and angular velocity or none of the above options? So let's say you have a global frame. You're sitting here, okay, and you see, let's say what it should be, let's say a pen falling under free fall. Okay, it someone has left the pen in the air and it starts to fall. If it starts to fall, and let's not consider any angular effect happening, it is just moving with a linear velocity. Let's not consider that there are moments by the air resistance force acting on the end, and it is just a linear motion that is happening in the z direction, negative z direction, basically along the lines of gravity. Then what happens there? You actually can see that okay, it is not moving, it does not have any angular velocity, but it just has a linear velocity. So being in the global frame, if a body is moving linearly, you will be always seeing the linear velocity, right? So answer is as simple as that. So since the orientation, I'll write it here, since the orientation is not changing with time, the rigid body is undergoing pure translational motion. Okay, so in translation motion, what happens? Every point on the rigid body moves with the same linear velocity and there is no rotation about any axis. Therefore the body has linear velocity and no angular velocity. All right, okay.
Ma'am, one doubt, ma'am. If the question is like, if we have a global fixed frame and a local fixed frame attached to the rigid body, then what will be the minimum number of degrees of freedom to define the position and the dimension of the rigid body in three-dimensional space? How will we determine this, ma'am?
You have a global fixed frame that is sitting somewhere else, and on the body you have a local frame, right? Um
Yes,
okay,
ma'am.
okay. You have a local frame on the body and you have a global frame, and then and what is the thing you want to define? Can you repeat the complete question?
And we have a global fixed frame and a local frame attached to the rigid body.
Hmm.
Then what will be the minimum number of degrees of freedom to define the position and the orientation of the rigid body in three-dimensional space?
Okay, then it should be 6 now, as we discussed, because we want to define both position and orientation. So the reason why I'm saying this is, so don't take the question to have global frame being attached on the rigid body. Only the local frame is attached on the rigid body. So there is a global frame with some origin sitting at somewhere in the room that you are in, and then there is a local frame which is attached on, let's say, a chair in your room. Then if it is moving in this 3D space, I won't say chair, let's say you have a drone in the room, okay, and it is able to reach any place, then it is definitely going to move in x, y and z, and it is going to have all the three orientations, phi, theta and psi. So minimum degrees of freedom that you need to define where it is actually located is going to be 6. All right,
Okay, ma'am, clear.
okay. Okay, then let's move to the 8th question. So yeah, if a rigid body has angular velocity, then due to this angular velocity, it also has what? So it is basically similar kind of question that we saw here, that we have a global fixed frame and a local fixed frame on the rigid body B. So, okay. Okay, so if a rigid body has angular velocity, then due to its angular velocity, it also has what? Does it have linear velocity also? Does it have just angular velocity, or does it have angular acceleration? That is a question we are asking. So what is angular velocity basically? Angular velocity describes what? It describes the rate at which rigid body rotates about an axis. Okay, you might also know, okay, before that, any point on the rigid body except the center of rotation moves in a circular path along the axis of rotation, right? The center point remains fixed, and everything apart from it actually moves in a circular path. When it moves in a circular path, this circular motion that we have, this circular motion results in a linear velocity. And how is that defined? So you get a linear velocity also on the rigid body. Omega is the angular velocity, r is the position vector from the axis of rotation to that point. Thus the body has both linear velocity and angular velocity. So it is already rotating, but then on the all the points of the on the body also have a linear velocity. So if we just talk about linear velocity, it is incorrect because the body cannot have a linear velocity alone without the angular velocity, without the corresponding angular velocity when rotating. So this rotation is only causing the linear velocity. It cannot have linear velocity without the angular velocity, right? Then angular velocity alone is incorrect because, okay, I'll write it. I'm just saying it could be a problem. Uh, cannot have linear velocity alone without the corresponding angular velocity in circular motion. That is understood, right? Circular motion. For angular velocity, it is incorrect because angular velocity alone implies rotation, which inherently causes linear velocity for points away from the axis. So just angular velocity is not correct because it actually implies linear motion for all the points. Okay, so the correct answer is both linear and angular velocity. Okay, yeah, another thing, this angular acceleration is also there in the option. So why it is incorrect? Angular velocity that we saw, rigid body has angular velocity, does not imply angular rotation, right? Unless rotation rate changes with time. So let's say you are rotating some your joint with some angle theta, okay, and that theta is constant, theta dot is constant, all right. तो अभी मैं बोल रही हूँ कि आई एम रोटेटिंग माई जॉइंट with 2 radians per second, okay. If I even change that, I make it to 4 radian per second, then again 2 radian per second, the joint acceleration changes. The change in joint velocity will actually cause an create angular acceleration, right? The change in joint velocity. But in our case, it is not happening because it is just angular velocity and it has nothing to do with angular acceleration because angular velocity is not changing. We have a question that it has an angular velocity only. Okay, So this is also wrong. So the only correct option is both linear and angular velocity. Okay. Now, yeah. If R is the rotation matrix, then the matrix R dot RT represents what? Okay. So I want you to think on this question. Think on this question for 2 minutes. What could this mean? R dot है मतलब R dot basically R is basically made of theta. I am differentiating it, then I am multiplying it with the rotation vector. What this could actually lead us to? So I wanted to think on this for 2 minutes, please, and tell me what could be the possible answer. I'll be back. Yeah. Okay. Got the answer? Any opinions? No opinion? How is that possible? Okay, let's start. So if R is a rotation matrix, then the matrix R dot R transpose represents what? So we know very well that R is the rotation matrix. Okay. What would R dot give me? It would basically represent how orientation is changing with time, right? Then what actually happens is So you will have to try this actually. When you check this now, r dot r transpose, you'll always get it to be equal to a skew symmetric matrix, and actually r dot r transpose gives you the angular velocity. And you know how it is represented? I'll show you. So you will have angular velocities along all the directions, right? So it happens like this is omega z, this is omega y. This is the matrix you get. So before that, before coming to the right option, why it is not just orientation of the link? Because orientation is just given by r and not its derivative r dot. So we definitely cross out this option, right? Then let's check the second option, position vector of the matrix. Position vector of the matrix is also incorrect because this matrix relates to rotational motion and not position, right? We have rotation matrix. This rotation matrix does not have any translation term, right, which we saw in the earlier classes, that it is a combination of rotation and transformation, but rotation was just a rotation matrix. It had no translation. So this is entirely related to rotation, so it is not related to position, so we definitely do not get position vector, right? The third option is acceleration matrix. R incorrect. Why it is incorrect? Because r dot rt it is. So if it is r dot, it is definitely differentiation of theta. Okay, so if it is a differentiation of theta, then it is definitely going to represent velocity and not acceleration. It is not the double differentiation we are looking at. So after crossing out all the options, we definitely have this thing remaining, and it is some related to angular velocity as well. But my point is that this is well established that when you multiply both of them, you actually get angular velocity, and it is represented by this skew symmetric matrix. All right, so take this down for your note. It is something new, I think you are seeing. So okay, I still want to work on this. What would be the, so this represents angular velocity, right? We already got the answer. Angular velocity matrix. But what would be the matrix for acceleration? That could be angular acceleration. So that is something we can look at. And yeah, I'm not going to derive it definitely, but I'll just tell you what happens here. So your angular velocity is given by r dot rt. Okay. If you differentiate it with respect to time, what I am saying is differentiate okay, when you differentiate it, you will get omega dot is equal to r double dot rt plus r dot t transpose. Okay, this is a thing that you are going to get, and it is your angular acceleration matrix given by omega dot. Okay. There is some meaning associated with both of these terms. I think I should tell you. So, yeah, it represents the change in angular velocity over time, right? So angular velocity change over time. This is all it is. This is a new extra term that is arising, and it arises from the product rule, because we actually had multiplication of omega r, we differentiated and everything from product rule. And what it represents rotational coupling effect. Okay, So if I wish to represent angular acceleration vector, it will look like this, similar to the skew symmetric matrix that we saw earlier. Okay, where all of these alpha x, alpha y and alpha z are the components of angular acceleration vector. Okay, so these are all the components of white color का. हाँ हाँ मैं एंड में ठीक है ठीक है ठीक है. हाँ वो वाइट वाला चार्जर. ठीक है. Okay, so this represents the angular acceleration vector. Okay, so it basically captures the rate of change of angular velocity. I hope it is clear. Now, okay, let's move to the next question. When a serial arm having n degrees of freedom is moving, okay, it has n degrees of freedom, then the angular velocity of the next link is what? Is it the sum of angular velocity of previous link and its own angular velocity? Is it its own angular velocity? Is it its linear velocity? Or is it its acceleration? Okay, so it is a serial manipulator. So I'll draw one serial manipulator over here. Let's say this is your serial manipulator. All right, this is some angle already here, theta 1. This is let's say theta 2. This is, let's say, theta 3. These three are there. Okay, so in a serial manipulator, each link's motion depends on previous link's motion, right? So if the way my theta 1 moves actually influences how my theta 2 is changing. No, it does not influence in a way that theta 1 45 है तो theta 1 theta 2 क्या रहेगा, but ultimately the end effector position which it actually relies on all of these three, theta 1, theta 2 and theta 3. So it is going to change, right? So each link motion, if I talk about this link, the topmost link, each link's motion depends on previous link's motion, right? The angular velocity of the next link is the sum of angular velocity is sum of what? One of the things is angular velocity of the previous link. So angular velocity propagates from base to the end effector through each joint, right? So definitely the angular velocity of the base frame and the links in between is going to have an effect on the end effector. The second thing is its own angular velocity. So each joint that we have, each joint introduces its own angular velocity, adding to the existing velocity from the previous link. Okay, so what we can write for link I plus 1, I can write omega I plus 1 is some omega I, which is from the previous link, plus theta dot I into zi plus 1. What are these things? Omega I is basically angular velocity of the previous link. Okay. Theta dot I plus 1 is your joint angular velocity. And zi plus 1 is your joint axis direction. Okay. So actually what happens is it is basically going to be sum of what? Sum of angular velocity of the previous link and its own angular velocity, right? So it is not just on it is not just on angular velocity, because just a second. Yeah, it's just not on angular velocity, because the next link angular velocity is not independent. It depends on previous link's motion. Also, it is incorrect because the linear velocity term is incorrect, because angular velocity and linear velocity are different concepts, right? So linear velocity results from rotational motion but does not define rotation itself. Okay, so no. And then acceleration, it is incorrect because acceleration is the rate of change of velocity and not the velocity itself. So the angular velocity has to depend on some quantity, but what is it? So it is the angular velocity of the previous link and just its own angular velocity. It has nothing to do with velocity, linear velocity or acceleration, or just own angular velocity, right? It is the combination of both the terms. So the correct answer is, it is the sum of angular velocity of the previous link and its own angular velocity, basically reflecting how the motion propagates through the serial chain. All right, I hope all of this makes sense. If it does, then let's move to the last problem that we have, and it's going to be a MATLAB problem. Okay, so our MATLAB problem is, let's say we are given a 7-DOF planar robot. Okay, let's say we are given a just a second. Yeah, 7-DOF planar robot, and then we want to compute the joint velocities to achieve the desired end effector velocity. So we need to have a desired end effector velocity. We want to compute the joint velocities to do that. We want to use the concept of pseudo inverse definitely to resolve redundancy problem, because we are anyway interested in a planar motion. So planar motion के लिए 7-DOF use करना is definitely going to make the robot independent, because in plane you will just have x, y and theta and nothing else, but you have 7 degrees of freedom. What will you do with 7 degrees of freedom? So you can use 7 degrees of freedom to do some more tasks. So let's say we want to achieve an orientation of all the links to be 45 degree with respect to each other. Let's say मेरा पहला link is 45 degree here, then the next link is 45 degree, 45 degree, 45 degree, 45 degree. How many I have done? 1 2 3 4 5 6 7. Let's say I want to achieve 45 degree angles with respect to each other. So it will help in reaching a particular uh, this posture. So the extra degrees of freedom can be utilized to do this. Otherwise, if you just want to reach your end effector to reach a particular point, it just needs 3 degrees of freedom. Even a 2-hour manipulator was able to do that. So everything that we have actually accounts for the singularity problem that you get when you reach the end of the workspace in 2-hour manipulator. Then also you are able to do some other tasks that you want to do. Okay. Also, what we want is to add a null space term to avoid obstacles or optimize posture. So what we'll be doing is we'll be optimizing posture. No avoidance obstacle will do. But we'll do something to optimize the posture, okay? That is what we are looking at. So today, before turning MATLAB on, actually I'll take you through the code. After taking you through the code, I'll go there. So okay, so what are the series of steps that we need to perform? First is definitely forward kinematics will come into picture, because we want to find what is the end effector position based on all the joint angles. Yeah, based on all the joint angles and link. Then definitely we need a Jacobian matrix, because we need to relate what is the joint velocity to the end effector velocity, right? Then the other thing we'll do is calculating the pseudo inverse. So pseudo inverse computes the joint velocities to achieve the desired end effector motion, right? So this J inverse, which is not inverse, it is pseudo inverse. So this pseudo inverse will actually help us in determining, okay, what is the joint velocity I need to find to get this end effector velocity. Then the other thing is we need some null space term. So the null space term is something that ensures that extra degrees of freedom are used to optimize posture, not avoid obstacle. Remove this for now. So it is just being used to optimize posture. So basically this term, this is the extra term you have, and it will be used to optimize the posture. Okay. And then for posture optimization, we drive the joint towards a desired configuration. Here it is 45 degree. Okay. Now let's see how do we go with it. So the key takeaways that you'll have from here is you get to know the concept of redundancy more of than what the task is actually requiring. So we'll be using them for posture optimization. Pseudo inverse, it provides a primary solution for the task fulfillment. Definitely you get to know what is the joint velocity you should have to achieve this in end effector velocity that you're talking about. And then null space basically uses extra degrees of freedom for secondary tasks, that is posture optimization. All right, now let's move to the code. Okay, you might have already seen that when I start the code, the very first thing I write is CLC clear and close all. Okay, what do they mean? Has anyone still found out a difference between all three of them? I mean, why do I write all three of them every time? Any idea? Are you all there in the call? Tell me if you know. If you know even about one of them, tell me. No one knows? How is this possible? You can answer in the chat box if you don't want to unmute yourself. That works. But do tell me, because we are doing the MATLAB session, I think you should have some benefit of of these sessions happening. I mean, if you're not enjoying MATLAB sessions, then do let me know. Then we'll just do the question answers. I'll increase the number of questions and answers, and we'll be dealing with that. I'm doing MATLAB problems because I want you to know MATLAB. So is this okay if I proceed with MATLAB every time? Or is there something that you want? I just want to know what is the poll of the audience so that I can make decisions accordingly from the next session. Guys, can you answer yes or no? My question is, shall we proceed with MATLAB every time? Just tell yes or no in the chat box also it works. It's just 5 of you. This time I will definitely do next time. I just want your honest opinion.
Ma'am, MATLAB is okay to do, but in the busy schedule, I think we'll not be getting enough time to go behind the MATLAB works and all. But at the end of the time, it will be useful, I think so.
Okay, so you
But
understand.
now, as of now, we are concentrating on the assignment completion and also to understand the concepts which is given by the professor.
Okay,
But
but
later on,
huh.
MATLAB will be useful.
Okay, then if you know the basic things also, no, that is happening in MATLAB, it would also be good for you. You'll have at least some familiarity with it. And moreover, all the codes that I'm using here, I'm already providing it. This time it is in the slide. The time it was not in the slide, it was already placed in the folder. So you can directly copy from here and paste it and use it and try to understand what all things are happening. You all also know Chat GPT, right? So give the code, tell it that explain everything. I know you have a busy schedule, but learning this in BTech will help you a lot. Or even if it is masters or any time actually this helps. So just doing the course and then finishing the assignments, getting the grades. Apart from that, if you are going to be roboticist, then you're going to apply all of these in real life. And when you're going to apply now, you'll need all of the codes. So and maybe you'll use Python. It's not necessary that you'll use MATLAB, but yeah, I would definitely suggest you that keep on listening and internalizing the things that are being covered, like MATLAB problems. It would be very helpful for you in the long run, very helpful. I mean, you get to see the results here, which you just keep on imagining that okay, this would happen, this would happen. When you play with the codes and all the angles and all the links, now you'll get to see what happens actually. So yeah, this would help. So that is why this time I'm having it on my this tab itself, and from here only I'll be taking you through all the lines, and after this we'll see the result on MATLAB window. Okay. So when it is CLC clear and close all, now CLC actually clears command window. Command window you saw where we get the result and we can access the variables directly. Then this clear actually uh, what it does, yeah, it clears all the data that was fed into variable from the previous run. ओके तो अभी एस में अगर कुछ डेटा डाला था एस इज इक्वल टू 20, नेक्स्ट रन करते समय एस में 20 ही स्टोर नहीं रहना चाहिए, इट शुड एक्चुअली गेट डिलीटेड, राइट? दैट इज वाई. एंड दिस क्लोज ऑल इज फॉर क्लोजिंग ऑल द विंडोज. Okay, now after this theta that we are defining is basically initial joint angle of the seven joint angles that we want for 7-DOF robot. So this is initial joint angle, and it is converted from degrees to radian using this dig to rad. So it helps you in converting from degrees to radian. N is basically the length of theta, and y is length of theta because we want to define what is the number of joints. So it is in this way. Okay. Then this link length is 1 n. Matlab I want the link length to be 1 and it should be n dimensional. So we assume link length to be 1. Okay. Now after this what will okay, so just say, yeah, this is your desired end effective velocity. So let's say we want to move horizontally to the right, because we have vx vy. So let's say we have x here, y here, and omega. Okay, so we want to move horizontally to the right. That means we want some velocity in the x, right? So that is why we desired is like this. Now we only have the velocity in the x direction. Then what we do, we try to calculate this forward kinematics. So forward kinematics is take argument L and theta and then give me what is x and y. So take the link length, take the theta, okay, so whatever theta is there, and then give me what is x and y. So that is all that is calculated from forward kinematics. I think I'll come to forward kinematics first before going somewhere else. So yeah, I think yeah, this is forward kinematics function. So what it actually does is this okay, you understand this, right? L into cos, okay, this is basically cumulative summation or sum. So it is cumulative sum of angles to get the total rotation of each link. So you know this, right, that if this is theta 1, if it is theta 2, if it is theta 3, then the total total orientation by which the robot's end effector has moved in planar setting is theta 1 plus theta 2 plus theta 3. You know this already, right? So this basically helps you in computing the cumulative sum of all the angles to get the total rotation of each link. For rotation of each link, okay, and it is multiplied by L to compute x and y coordinates of each joint. That is why it is there in this way. All right, now when you understand this, then we can go to the next step. Here we can compute the Jacobian. Now I had already told you Jacobian is a function which is directly available. Last time we had gone through this, and it can be directly used. But let's this time what I've done is I have implemented it as a function. So let's see the function. Okay, so it basically computes a Jacobian matrix relating joint velocities to the end effector velocities. That is what we want to do here. So it is like partial derivative. Okay, we want to take partial derivative, right? So let's say we have n length of theta only, that means the number of links, and z or j orientation you already defined. So let's say x, y and theta are the things that we want to optimize. We have a Jacobian matrix over here. Okay, and then you have the orientation things over here. Okay, so we have defined Jacobian to be in this way, and then we want j1i to be I mean basically the differentiation thing is happening over here. All right, orientation part we make it to be constant because it is a planar manipulator, and let's say orientation part is not there. If it is there, not there, that does not matter. It is anyway making the same sense. Matlab, if you write theta to be equal to theta, what sense does it make? So if you even remove this, it would just be a 2 cross 3 matrix, 2 cross n matrix. But for now we have taken 3 cross n matrix. So it is basically the way in which you define and nothing else. Okay, and then we find out what is the partial derivative, and this is the function for calculating the Jacobian. So no matter what the programming language is, the way in which you define the way the logic remains the same, always remains the same. You're supposed to differentiate it, define a matrix, differentiate all the terms with respect to the other variables, and find out the partial derivative. Okay, so here you have calculated the partial derivatives for each joint angle. Now let's move to the next step, that we actually want to take pseudo inverse. Okay, so this we had already discussed, right? Pseudo inverse of j. So this is the pseudo inverse we are taking because the Jacobian matrix in our case is right now 3 cross 7 matrix. So this is what we are doing. Now after this we calculate theta dot is equal to pseudo inverse of j into desired velocity. So we already know this relation, right? J inverse x dot. Here in this case, this is a pseudo inverse. Okay, so this is pseudo inverse, and theta dot is the joint velocity required to achieve the desired end effector velocity. So this is all we have. Okay, after this, what we are doing is okay. After this, what we are doing is we want to have a null space term for posture optimization. So you already saw what is null space, right? This part. This is my null space part that we want to have for posture optimization. Okay. So what we are doing is, yeah. So in this case, okay. This is null space projector, and it is given by I minus j pseudo inverse. So let's take it this way, j. That is all we want to find out, and then we want to define that my posture task is to achieve 45 degrees. So what I want at the end of the day, that my manipulator should all of these should achieve, drive all the joints towards 45 degrees. Okay, this is what we want. And then n into posture task basically ensures that this optimization does not affect the end effector motion. Okay, gain is just to influence the posture goal. अगर इसको 1 करेंगे तो जल्दी जाएगा, अगर इसको कम रखेंगे तो we are not maintaining a strong pull. Let's say we keep it to be 0.1, then we are not maintaining a strong pull. I think you should read upon this, that how we do with this null space projection, so it would help. Okay, after this what we want to do is we want to display the results of joint velocities, because we had this end effector velocity already given. We found out the Jacobian, and then this is only the remaining term that we want to find. So we found this out also. Okay, after doing this, we'll plot the manipulator, current manipulator, because we have found out the joint velocity, right? So from there we can find out joint angles theta. Okay, for this theta we'll plot the current manipulator, and we'll also plot this 45-degree posture. So the plot for it is also given here. And then once this all of these is done, we just go for plot function, where this plot function basically plots the 7th planar redundant manipulator and includes both of the plots that we want to do here. Okay, both these plots, this plot and this plot, both of these in one. So I'll show that to you. Before that, since I'm not going to switch the screen back here, key takeaways from this task is your primary task is end effector reaches the desired velocity. What is your secondary task? That you have some extra degrees of freedom to optimize posture towards 45 degree, and yeah, you are able to visualize current and target configurations. Now I'll switch my screen to the MATLAB screen and show you what is happening. I'll change my screen to MATLAB. Okay. Rather meet screen, I'll change it to meet screen. Okay. I think I'll have to change it to MATLAB only. Okay, I'll switch to MATLAB. Okay, so this is the MATLAB code that I already showed you right now. It has the same thing written over here. I just copied from here and pasted it there. And when you run it, you can see. I hope this is visible. Are you able to make some sense out of whatever is shown? Okay, so yeah, where is the figure? Yeah. So this is your current manipulator. See, it has 7 degrees of freedom, and then we wanted it to move with a particular velocity. But yeah, definitely I have not made animations. From here you can see that it turns and turns with the same velocity and it comes to this final orientation. So I've not made an animation out of it, but you see that how it is driven to 45 degrees using the extra degrees of freedom while maintaining the same end effector velocity. So you decided what is the joint velocity, you decided what is the posture, you decided what is the end effector velocity you need, and then you got it. All right. I hope this makes sense. Then I'll close it. Okay. I hope everything was clear. And yeah, we'll have this time it is on, today's lecture was on Tuesday. Next time we'll have again everything from Monday only. It's not going to be on Tuesday. It is going to be the same schedule, 6 to 8 p.m. From on Monday. And yeah, so see you next Monday. If you have any questions, you can ask, else we can leave.
Thank you, ma'am.
Okay. Okay, so I think you have a folder, right, already here. Just a second. So I think this folder is already available, accessible to you, right? So I'll be uploading the code here itself in this folder. In this presentation folder that we have, I'll be uploading it here. In your dashboard that you have for NPTEL, you have the recordings of the lecture. I mean, this sheet is available to you. From here, you can access the recordings and you can also access this presentation folder link. Here you'll have the code as well. I'll put it there, MATLAB code. All right. And moreover, I'm anyway going to share this PPT that I already wrote on. So that also has a code. So you can directly take the code from there. It is not even required to upload it again. You can just copy it from there and you can use it. All right. One more thing I'll do is I'll just, for your convenience, I'll copy the code and uh, where is it? I'll just paste it here for your convenience so that you can directly take it from here. I don't know. I think no, I cannot send the whole code here. You'll have to get it from the slides only. It just comes for some lines only. Plot the manipulator and target. Okay, from here. So I think indentation could also be a problem for you. Yeah, I think the code is not completely done. Wait. Yeah, I have all the code pasted over here. You can just copy it from here, but we might have lost on the like indentation and all. So you can refer to the PPT that I'll uploading. That will help you in correcting everything, in matching and doing the corrections wherever required. Okay. So yeah, we are done with the lecture.
Ma'am, if it is okay, can you please send the link of the recordings today itself? I got some miss in between, so that I can catch up with it today itself.
So yeah, I'll be uploading it in this sheet. All right. I hope you
Okay,
have
ma'am.
the access to this sheet.
Yeah, ma'am.
Yeah, so I'll be uploading it here right in like half an hour or so.
Okay, ma'am. Thank you. Thanks a lot.
Okay. Thank you. एक मिनट